Good morning, friends. Already we discussed about the half-life of a radioactive element. We define and also we derive the relation of half-life of a radioactive element with respect to with decay constant. That means the tau half is equal to 0.693 upon lambda. There is the relation between half-life of a radioactive element with the decay constant. Okay. Now, what is the definition of half-life? The time duration or the time interval during which the number of radioactive nuclei in a radioactive element becomes the half of its initial value. Such time interval is known as half-life time of a radioactive element. Okay. After the discussion and derivation of the equation of half-life, now we are going to discuss about what is the mean life or average life of a radioactive element. Right? Now listen one more thing. In old textbook, the derivation of average life is different than the NCERT book. Therefore, we are considering this new method to derive the relation between average life and decay constant. Here the integration method is considered, right, in NCERT textbook. Okay. Now, first thing, what is the definition of average life and derive the relation of average life with decay constant and half-life. Again, the question is that define average life or mean life of radioactive sample and derive its relation with decay constant and half-life. So first, what is the definition of average life or the average lifetime? The time duration for which the nucleus exists, that is known as the average life of a nucleus or radioactive sample. We know that the heavy nuclei initially is in unstable state. Try to acquire the stable state. For that purpose, it emitting either alpha, beta or the gamma. So this way, the unstable nuclei, heavy nuclei, try to obtain the stable state. So due to the emission of alpha, beta and gamma, so its atomic number and atomic mass is going to decrease. That means this nucleus is converted into the other nucleus. So whatever time taken by the nucleus for which it exists, that is known as the average life of a nucleus. Now, this question is also asked in other way. Define the mean life of a radioactive sample and obtain the relation tau is equal to 1 upon lambda. There is the relation between mean life and decay constant. Or tau is equal to 1.44 tau. There is the relation between the average life with the half-life. Okay. Now the definition of average life is that the time interval for which the nucleus exists is known as average life of a radioactive element. Is known as average life of radioactive element. Again, the time interval for which nucleus exists is known as average life of radioactive sample. Other definition, same as the half-life. In half-life of a radioactive sample, the time interval during which the number of nuclei in a radioactive sample becomes the half of its initial value. The same manner, the definition of average life is that the time interval during which the number of nuclei in radioactive sample becomes ith part of its initial value. So the other definition is that the time interval during which the number of nuclei of radioactive element becomes ith part of its initial value. Such time is known as mean life or mean life of a radioactive sample. Again, the first definition is that the time interval for which nucleus exists. Or the other definition is that the time interval during which the number of nuclei in a radioactive sample becomes each part of its initial value. Such time interval is known as mean life of a radioactive sample. Clear this? So, from this definition, the average life is defined by tau. The average life is defined by tau. Half-life is defined by the tau half, while the average life is only defined by the tau. So, according to our definition, our equation of average value, so average lifetime tau is equal to sum of lifetime of all nucleus divided by number of total nuclei. How we find out the average of 4 observations? Suppose the 4 observations of length. So L1 plus L2 plus L3 plus L4 divided by number of observations. So here the same thing. Average lifetime tau is equal to sum of lifetime of all nucleus divided by number of total nucleus. Right? Using this concept, now suppose at time t is equal to 0, the number of nuclei in a sample is n0, and at time t, the number of nuclei is n. And dn is the number of nuclei are decay in time interval delta t. To derive the equation of average life, we assume that suppose at time t is equal to 0, the number of nuclei in a radioactive sample is n0. At time t is equal to 0. And at time t, any time t, the number of nuclei is n. While dn is the number of nuclei decay in delta t time. In delta t. Right? If the lifetime of each nuclei, if the lifetime of each nuclei is t, therefore the total lifetime of dn nuclei, one nucleus has the lifetime is t, therefore the dn nuclei has the lifetime is t into dn, t into dn. Therefore total lifetime of n0 nuclei at time t is equal to 0, we have the total number of nuclei are n0. So what is the total lifetime or the sum of lifetime of all n0 nuclei is the sum of t dn1 plus t dn plus t dn. How many times? n0 times. Therefore we take the integration from 0 to n0 t into dn. Right? There is the total lifetime of all n0 nuclei is integration from 0 to n0 to t into dn. Therefore, average lifetime is equal to total lifetime of n0 nucleus divided by number of nucleus. Therefore, total lifetime of n0 nucleus divided by n0. Therefore, average lifetime tau is equal to integration 0 to n0 t dn upon n0. So that can be written as 1 upon n0 integration 0 to n0 t dn, equation number 1. Now we have to take the integration of this term. But here the function is in term of t while the variable is n. We have to convert this variable n into t. For that purpose, the exponential law of decay or the radioactive decay is n is equal to n0 e is to minus lambda t. N is equal to n0 e is to minus lambda t. As the time changes, the number of nuclei in a radioactive sample also changes. Therefore, the change in time t is delta t. Therefore, the number of nuclei is changed by dn. N is changed into dn. Therefore, taking the derivative on both sides, left hand side with respect to n, while the right hand side with respect to t. Therefore, the change in n is dn. dn is the number of nuclei decay in time interval delta t over the decay. Okay. Here n0 is constant, derivative of e⁻² minus lambda t. e⁻² x as the derivative is also e⁻x. But here, the derivative of this part is also considered. n0 is constant, derivative of e⁻² minus lambda t is also same as. And now, the derivative of minus lambda t with respect to t is also minus lambda. Therefore, minus lambda n0 e⁻² minus lambda t into dt. So, derivative of this term is similar to this way. d by dt of e⁻xt is equal to e⁻x as it is. Derivative of this term xt is equal to e⁻x into x. This method we are using to take the derivative of e⁻² minus lambda t. n0 is already constant. Derivative of e⁻² minus lambda t is same as. Now derivative of lambda t is minus lambda, like this method. Therefore, we obtain minus lambda n0 e⁻² minus lambda t into dt. That is the value of dn. Substitute in equation 1 here. Therefore, if this like tau is equal to 1 upon n0 as it is. Now, integration 0 to n0 as it is and t as it is. Now, instead of the dn, minus lambda, this minus lambda, n0 e⁻² minus lambda t into dt. This n0 is cancelled with this. Therefore, a base like tau is equal to minus sign taken out, integration 0 to n0 e⁻² minus lambda t into lambda into t. So, lambda as it is, e⁻² minus lambda t and dt. Lambda is taken out because right hand side is now function of t and variable is also t. Therefore, integration 0 to n0 t into e⁻² minus lambda t into dt. Minus lambda is taken out. Okay. So now in integration, there is the limit, lower limit, there is the upper limit. If we interchange the limit, so the value of integration becomes the negative. Here the limit is 0 to n0. Yes, we add n0 to 0, so that becomes the negative, like this way. If a to b a dx or the y dx is equal to minus integration b to a y dx. If we change the limit upper as lower and lower as upper, so its value becomes the negative. Here negative sign already exists. If we change the limit from 0 to n0, instead of this, we can add the n0 to 0, its value becomes the again negative, this negative positive. Therefore, lambda is taken out. Now the limit is changed n0 to 0, t e⁻² minus lambda t into t. Clear this? Okay. Now initially we consider at time t is equal to 0, number of nuclei in a radioactive element is n0. Therefore, when the value of n is equal to n0, at that time t is equal to 0. And when the total nuclei are decay in a radioactive sample, how much time taken by the nucleus? So there is the infinite time, because the no any nuclei is completely becomes the non-active. Never becomes the non-active. That is the for long time it is the active. That means they are decaying. That means they emitting the some energy. Therefore, as the n becomes the 0, at the time taken is infinite time. So in this limit, when the n0, n is equal to n0, at that time t is equal to 0. And when the n becomes the 0, at that time t is equal to infinite. Now listen carefully. In this integration, the N0 and 0 value are the value of nuclei. But here, the right hand side is the function of time. Therefore, we have to change this value, lower and upper, in terms of the time, instead of the number of nuclei. N0 and 0 represent the number of nuclei. We have to convert into the time. Therefore, when the nucleus n is equal to n0, at that time the time t is equal to 0. And when the number of nuclei becomes the 0, for that the time taken by the nucleus is infinite. Therefore, n0 is equal to n0, corresponding to that the time is equal to 0. And when the number of nuclei becomes the 0, corresponding time is infinite. Therefore, this equation is written as tau is equal to lambda as it is. Now our limit changes from, instead of the 0, now 0. Instead of the n0, now 0. 0 to infinite t is 2 minus lambda t into dt. That is equation number 2. So there is a quite difficult because still your concept about the integration is not clear. Again I repeat it. So suppose at time t is equal to 0, then above nuclei in the radioactive element is n0. And at time t, number of nuclei is n. While the dn is the number of nuclei are decay in time interval dt. If the lifetime of each nuclei, not always only life of a nuclei is t, therefore total life, that is the sum of life of dn nuclei, is dn times t plus t plus t, therefore t into dn. Therefore, in a nucleus at time t is equal to 0 is n0, therefore total lifetime of n0 nuclei is, we have to take the integration of this term from 0 to n0, therefore 0 to n0 t into dn. T into dn. Now our definition of average lifetime. Average lifetime is equal to total lifetime of n0 nuclei divided by number of nuclei. Therefore, average life tau is equal to 1 upon n0 integration 0 to n0 t into dn. Equation 1. Here we have to substitute the value of dn. For that purpose, we are using the exponential law of decay. N is equal to n0 t is to minus lambda t. Taking the derivative, relative derivative on both sides. Left hand side with respect to n, right hand side with respect to t. Therefore, n changes to dn as the time changes to dt. Therefore, n0 as it is, derivative of e is to minus lambda t. E is to minus lambda t as it is, and derivation of lambda t is only minus lambda. Therefore, n0 minus lambda e is to minus lambda t into dt. Substitute in equation 1, therefore tau is equal to 1 upon n0, integration 0 to n0, t as it is. Now, value of dn minus lambda n0 is to minus lambda t into dt. n0 cancel, therefore minus integration from 0 to n0, lambda is to minus lambda t into t into dt. So here the minus lambda is common. Integration from 0 to n0, t into e is to minus lambda t into dt. Now we change the limit upper to lower, lower to upper. Therefore the value of this integration becomes the negative. Already negative present, therefore this negative becomes the positive. Therefore lambda into bracket integration from n0 to 0 now. T into e is to minus lambda t into t. Right? Okay. Now this limit represents the number of nuclei. We have to change this limit in time. Therefore, when the number of nuclei is n0, there is the initial condition at that time t is equal to 0. When the number of nuclei in a radioactive element completely vanishes, that means the completely becomes the zero. The time taken by the sample is infinite. Therefore, 0 to infinite, tau is equal to lambda integration from 0 to infinite t into e is to minus lambda t into dt. That is the equation 2. Clear? Okay. Now we take the integration. Now second equation is tau is equal to lambda integration 0 to infinite t into e is to minus lambda t into dt. That is the equation number 2, right? Okay. Tau is equal to lambda 0 to infinite t into e is to minus lambda t into dt. Clear? Okay. Now we have to take the integration of this equation. Lambda is common. Therefore, t into e is to minus lambda t upon minus lambda. T as it is, integration of e is to minus lambda t. 0 to infinite. Minus 0 to infinite e is to minus lambda t upon minus lambda into d. Now, lambda is taken common, or first we substitute the value of t. Therefore, that becomes the 0. First term becomes the 0. And we substitute the value of upper and lower value of t as 0 and infinite. So, lambda into bracket 0. This negative positive 1 upon lambda as it is. 0 to infinite is to minus lambda t into dt. Right? Again, our equation 2 is tau is equal to lambda 0 to infinite t into e is to minus lambda t into dt. Right? Simplification of this equation is lambda as it is common into bracket. Now first term t into e is to minus lambda t. Due to this, therefore minus lambda value varies from 0 to infinite. Minus 0 to infinite e is to minus lambda t upon minus lambda into dt. Integration is taken by the integration of by parts. Law of integration by part. Now, as we substitute the value of lambda from 0 to infinite, so first term becomes the 0. Now, this negative positive 1 upon lambda as it is. Now, 0 to infinite e is to minus lambda t into dt. Therefore, this lambda cancel, lambda upon lambda, e is to infinite, e is to minus lambda t into dt. This lambda cancel. So, we have only the top is 0 to infinite, e is to minus lambda t into dt. Now integration of this term. Same as integration of e is to x into dt. Or as we write the e is to lambda t into dt. So its integration is e is to lambda t, and of lambda t is this only lambda. Right? Therefore, integration of this term e is to minus lambda into t into dt is equal to e is to minus lambda t upon minus lambda. Value varies from 0 to infinite. So is equal to minus 1 upon lambda. This lambda is taken out. Now we substitute the t as first infinite minus t as 0. Therefore, integration e is to minus infinite minus e is to 0. E is to 0 is 1, e is to infinite is 0. Therefore, minus 1 upon lambda into bracket 0 minus 1 is equal to 1 upon lambda. Therefore, the relation between average line tau is equal to 1 upon lambda. Relation between a phase life and decay constant is tau is equal to 1 upon lambda. Right? Okay. Now we know that the decay constant lambda is equal to 0.693 upon tau half. Because already we obtained the tau half is equal to 0.693 upon lambda. We substitute the value of lambda in equation 3. Therefore, tau is equal to tau half upon 0.693. Therefore, tau is equal to 1 upon 0.693 is 1.44 tau half. Therefore, tau is equal to 1.44 tau half. That is our equation 4. There is a relation between the average life and half-life. Clear? Again, I repeat, the equation 2 is average life tau is equal to lambda into integration 0 to infinite t into e raised to minus lambda t into dt. Now we are taking the integration of this term. Lambda as it is, t into e raised to minus lambda t and divided by minus lambda 0 to infinite minus integration 0 to infinite e raised to minus lambda t upon minus lambda into dt. This integration is taken by the law of integration by parts. Now, lambda as it is outside. Now, as we substitute the value of t as 0 and infinite, first term becomes the 0. This minus minus plus 1 upon lambda integration 0 to infinite is to minus lambda t into dt. Now, lambda into this lambda cancel, remaining this term only 0 to infinite is to minus lambda t into dt. Clear? Okay. Now the integration of this term according to this equation is to lambda t into dt is equal to is to lambda t as it is, and now this. There is the 1 upon lambda. Okay. Now, so according to this equation is to minus lambda t upon minus lambda, value raised from 0 to infinite, minus 1 upon lambda is outside of this bracket. Substitute the value of t as infinite minus value of t as 0. So minus 1 upon lambda into bracket is to minus infinite minus e is to 0. Its value becomes the 0 and that is the value is 1. Therefore, minus 1 upon lambda, first term 0, minus second term 1. Therefore, minus minus plus 1 upon lambda. Therefore, average life is equal to 1 upon lambda, that means the decay constant. So that is the relation between average life and decay constant. Now, we know that the half-life tau half is equal to 0.693 upon lambda. Using this concept, lambda is equal to 0.693 upon tau half. Substitute the value of lambda in equation 3, therefore tau is equal to 1 upon 0.693 into tau half. That means the tau half upon 0.693. The simplification of 1 upon 0.693 is 1.44 tau half. So there is the relation between average life with half-life of a radioactive sugar. Here this. Here the integration is new for you. Therefore there is the quite tough. Otherwise very easy. Okay. Now after that, the next topic is the alpha decay, beta decay and gamma decay. Already there is cancelled for only board exam, not for the good set, NEET or the JEE. And for that purpose we are considering also the alpha decay, beta decay and gamma decay. That is also important for us to handle the equation of nuclear process. And due to that result, the understanding about the alpha decay, beta decay and gamma decay is required. If the any nuclei is emit the alpha decay, so whatever the new formed nuclei, the same way for the beta decay and for gamma decay. Okay. Now the question is that explain alpha decay and give its appropriate example. What is the alpha decay? In alpha decay process, the unstable nuclei emits the alpha particle, right, and automatically convert into new nuclei. Heavy nuclei is unstable. It has the tendency to obtain the stability. To obtain the stability, it first emits the alpha particle. Yeah. Yes, the alpha particle are emitted from the unstable nuclei. So it automatically converts into the new nuclei. Alpha particle is the nucleus of the helium. Therefore, instead of the alpha particle, we have to write down the 2He4 helium nucleus. Alpha particle is the nuclei of helium. Therefore, during the disintegration nucleus, the disintegrating nucleus is known as the parent nucleus, and newly formed nuclei is known as the daughter nucleus. During the decay process, whatever the nucleus is disintegrated, such nucleus is known as the parent nucleus. And whatever the newly formed nuclei, that is known as daughter nuclei. Okay. In alpha decay, the atomic mass number of daughter nucleus is decreased by 4 and atomic number is decreased by 2. That means in alpha decay process, the atomic mass number of daughter nuclei is 4 less and the atomic number is 2 less than that of parent nucleus. Whatever the newly formed nuclei, there is the daughter nuclei. Yes, the atomic number is decreased by 2 and atomic mass number is decreased by 4 than the parent nucleus. Clear? Okay. The equation of the alpha decay is the general equation for alpha decay process XZA. X is the element that is known as the parent element. Newly formed element is 1. Having the atomic number is decreased by 2, that means the Z minus 2, and atomic mass number is also decreased by 4, therefore A minus 4. And there is the alpha particle is emitted, therefore the helium nucleus 2He4, and some amount of the energy is also released, that is the Q value. Again, the example of the alpha decay, XZA converts into the daughter element Y, Z minus 2, A minus 4. And the alpha particle is produced, that means the helium nucleus is formed 2He4 plus Q value are emitted. Here the X is the parent nucleus, Y is daughter nucleus, and Q is the total kinetic energy of the product. How we calculate the Q? By Einstein's mass energy relation, Q is equal to delta m c square. Delta m is the mass difference. So here Q is equal to mx, mass of the parent nucleus minus mass of the daughter element minus mass of the product, into bracket c square. That is our mass difference. Again, Q is equal to mass of parent nucleus minus mass of daughter nucleus, mass of alpha particle into c square. Okay. Clear this thing? Okay. In original nucleus is at rest. If the original nucleus is at rest, therefore the Q is kinetic energy of the product. Q is not obtained as a bunch of energy. That is generally obtained in form of heat energy and also in form of kinetic energy of the product. If the original nucleus is at rest, so Q is total kinetic energy of product. Now here the two types of the alpha decay process take place. If the Q is greater than 0 for alpha decay, such process is known as the exothermic process. And if the Q is less than 0, value of the Q is less than 0, the process is known as the endothermic process. If the Q is less than 0, the process is known as endothermic process. Now the example of alpha decay from uranium nucleus. Uranium nucleus is the heavy nucleus 92 to 38. When the alpha decay takes place, at that time this uranium nucleus is converted into the thorium 90 to 34 plus helium nucleus format plus Q amount of the energy is also released. This Q amount of the energy, Q is equal to mass of uranium nucleus minus mass of thorium minus mass of helium into C square. Clear this? Okay. Again we will the alpha decay. In alpha decay process, the unstable nucleus emits the alpha particle and automatically convert into new nucleus. Alpha particle is the nucleus of the helium, therefore alpha is equal to 2He4. Now the heavy nucleus is disintegrated itself, right? Therefore the disintegrating nucleus is known as the parent nucleus and newly formed nucleus is called the daughter nucleus. Okay. In alpha decay, during the alpha decay process, the atomic mass number of the daughter nucleus is less 4 less, and atomic number is 2 less than that of parent nucleus. Now the general example of alpha decay is that XZA convert into the Y, Z minus 2, A minus 4 plus 2He4 helium nucleus plus Q amount of energy. X is known as the parent elements, Y is known as the daughter element, 2He4 are the helium nucleus and Q is the kinetic energy released. Therefore, how much energy is released? So, according to the Einstein's the mass energy relation, Q is equal to delta MC square, delta M is the mass defect. Therefore, Q is equal to mass defect, mass of the parent element minus mass of the daughter element minus mass of the product, that means the helium nucleus, into C square. Right? If the orbital nucleus is initially at rest position, therefore Q is obtained in form of kinetic energy of product. Here the two types of the alpha decay take place. If the Q is greater than 0, so that is known as the exothermic process. And if Q is less than 0, this process is known as the endothermic process. Now, the example of alpha decay. Uranium nucleus 92 to 38 is unstable. After the alpha decay, it converts into the thorium nucleus 9234 plus 2He4 helium nucleus, that means the alpha decay plus Q value. Q value obtained during this process is Q is equal to mass of the uranium nucleus minus mass of thorium minus mass of the helium into C square. So this is the alpha decay.